Okay, we start again our class from dummy variable model. Okay, I explained already that in the regressions model, we can use ratio scale, interval scale, ordinal scale, and nominal scale. Okay, but in the preceding class, we usually use ratio scale in our variables. Okay.
Sir, sorry to interrupt you again, but the screen is gone. Now we can see it again. Sorry.
Okay. Okay. Because not all of variables are in term ratio scale, because there are also in qualitative variables. So, for example, for the gender, educational level, working status, okay, regions, etc. Okay. Okay, in the regression analysis, dependent variable or regression is frequently influenced not only by ratio scale variable, such as income, output, biases, etc., but also determined by qualitative variables, okay, such as regions, political affiliations, and so on. Okay. So those variables are represented by dummy variables. Okay. So this one, if we use all dummy variables in our model, except for dependent variable, this means we use analysis of variant. But if there is one of the variable of independent variable is ratio scale variable, so we call it ANCOVA, analysis of covariance. This is for illustration of ANOVA model. Okay, we use data in table 9.1. The data give us about the average salary in the 50 states of United States and one district of Columbia for the academic year 2005 until 2006. These 50 areas are classified into 3 geographical regions. One for Northeast and North Central. This area has 21 states. And second is South with 17 states. And the last one is West area. In this area, there are 13 states. For time being, do not worry about the format of the table and the other data given in the table. Suppose we want to find out if the average annual salary of public school teachers differ among the 3 geographical regions of the country. So if we take the simple arithmetic means of the salary, we can get that the highest average salary is in the Northeast and North Central area, and the second is in the West area, and the last is in the South area. This number look different, but in terms of regression model, we have to test whether there is a difference between regions 1 with region 2, and region 1 and region 3, region 2 with region 3. So we use here analysis of variance for the model. The model is stated in equation 9 to 1. Okay, 9 to 1. Okay, 9 to 1, yeah. Okay, we have dependent variable is average salary of the public school teacher in the in each stage, and D2 represent the dummy for area of northeast and north central. Meanwhile, dummy 3 is a dummy for south area. Okay, because we have 3 dummies, so we cannot include all dummies in our model, because if we estimate the equation with all 3 dummies, we will have perfect multicollinearity. This means we cannot calculate the parameters of the model. So to avoid this problem, we have to drop one of the dummy variables. The dummy variable is not included in the equation, will be represented by the constant term. So the constant term is the value for the region is not in the model. However, we can also run for the all dummy variables in the model, but we have to delete the intercept term in the model. So here we have 2 options. If you want to include all the dummies, you must take down the intercept term. But if you want to drop one dummy variables, this means you can include the constant term. Okay. Here the data you can see by yourself here. Here, for example, here Connecticut is the second area. That's mean in the south one. Okay, this means we put one here for this area. This is salary of a teacher in this area. This is a spending, and this D1. And because this area is not linked to the west area, so the west is 0 here, etc. And so on. We have here Illinois. This is also in the south area. For example, here we have Georgia in the west area, okay, Kentucky in the west area, and so on. So we have this data. Okay. Equation 922 is telling us about the mean salary in the north and northeast and north central area, because here we take the dummy 1, dummy 2 is 1, dummy 3 is 0. Mean salary of public security in the south, okay, become this one. If D2 is 0, D3 is 1. So we take summation of beta 1 plus beta 2 to represent northeast and north central, and we add beta 1 with beta 3 to get the mean salary of teacher in the south area. Okay. Meanwhile, okay, because we do not include the west area in our model, so we use beta 1, the intercept term, to represent the mean salary of the public teachers in the west area. So west area is beta 1 plus beta 2 is northeast and north central, beta 1 plus beta 3 is south area. Okay, in other words, the mean salary of public school teacher in the West is given by the intercept term beta 1 in the multiple regression model in 921, and the slope coefficient beta 2 plus beta 3 tell by how much the mean salary of teachers in the northeast and north central area. Meanwhile, in the south is the south beta 1 plus beta 2. Okay. here we get these equations. Okay, T is a T ratio. Okay, this one indicate the probability value. If we see here, none of parameter is statistically significant. Okay, this regressions results show that mean salary of teachers in West is about 48. This one beta 1 represent the salary of West area, and meanwhile Northeast, North Central is high, about 1,500 something. This is the coefficient here. Okay, and for the South area is lower because it's negative here. We subtract 14 something minus 1,000 something. The actual mean salary in the last two regions can be easily obtained by adding these differential salaries to the mean salaries of teacher in the West area. This is mean salary in the West area. So equation 923 and 924 can be used to calculate the average salary of each region. Okay, by having this, we will find the mean salary in the latter two regions are about 49 something, 500 something. This is mean from 40x thousand plus 1.5 thousand. This mean 49,500 something. And the another one is 48,000 minus 1.7 thousand. We get 46 something thousands. But how we do know that these mean salary are statistically different from the mean salary of teachers in the West area? Because West area is benchmarked. We use beta 1 as a benchmarking to compare the salary between these regions. Okay, that is easy enough. All we have to do is to find out if the teacher, if the slope value of the equation is statistically significant. That's when we can add the constant with the slope. Okay. However, in our estimated equation in 9 to 5, we have here D2 is not statistically significant because the coefficient has probability value is greater than 0.05, and the third dummy also has p-value greater than 5%. This means those dummy variables are not statistically significant. Okay. Okay. You can read here. The estimated slope coefficient for Northeast and North Central is not statistically significant because the probability value is 52%. Meanwhile, in the South also is not significant because it has 49%. Therefore, the overall conclusion is that statistically mean salary of public teacher in the West, Northeast, and the Central and South is almost the same. So this is the functions of dummy variable. We can use it to compare one area with another. Okay. As question is, in order to interpret these differences, the dummy variable will simply point out the different if exists, but they do not suggest the reason for the differences because differences in the educational level, cost of living, indexes, genders, and a race might all have some effect on the observed differences. Therefore, unless we take into account all other variables that might affect the teacher's salary, we can compare whether there is a statistically significant between northeast and north central area to west area and to south area. Okay, here if we get that the coefficient, slope coefficient are statistically significant, we can add this one. Okay, here we see that the average salary for northeast, north central, this mean here 49,000. Okay, this one for the west, this is for the south. Caution in the use of dummy variables. Okay, although they are easy to incorporate in the regression model, one must use the dummy variable carefully, because I have mentioned already, if we include all dummy variables in our model, we call it dummy trap. Dummy traps means we will have perfect multicollinearity among the dummy variables. Okay. For example, here we have equation 926. We add all dummies in our model, include the constant term alpha. Okay, here dummy 1, 1 for state in the west, 0 for otherwise. Now we have a dummy variable for each of 3 geographical regions using data in the 9.1. If you were to run the regression 926, the computer will refuse to run because there is a perfect multicollinearity, and we cannot calculate beta because the determinant of x prime x is equal to 0. Okay. Imagine that now we add the dummy 1 column, taking the value 1, whatever the state in the west and the otherwise. Now we add the dummy columns horizontally, we will obtain ones for every single state. So we have 1 from the first state until the 51st states. Okay. But since the value of alpha's interceptum is also 1 for each operation, we will have the same column that also contain 51s. In other words, the sum of the 3 dummy columns will simply produce the same value of the interceptum. So this will cause perfect multicollinearity in our model. If there is a perfect multicollinearity, so we cannot estimate the parameters. Okay. The message here is that if a qualitative variable has m categories, you have to use m-1 dummy variable in your model unless you drop the constant term in your model. So because we have our 3 regions in our sample, so we have only 2 dummy regions. Okay, if you do not do if you include all the dummy variables, we call it a dummy variable trap. In these situations, we have perfect multicollinearity in our model. So it is impossible to get the asymmetric coefficient for the regression model of 9 to 6. Okay? For each qualitative regressions, the number of dummy variables introduced must be less 1, okay, because we have to avoid the problem of multicollinearity. Okay, the category for which no dummy variable is assigned is known as base, benchmark, control, comparisons, reference, or omitted category. So here, because we do not include the west area, so the beta 1 represent the western region in our model. Okay, so we use beta 1 as benchmarking to compare it with other region. Okay, this is a question. If you add all, we use all of dummy variables, you must drop the intercept terms as equation 9 to 7. Okay. Okay, here from the equation 9 to 7, you have beta 1 is the salary in the west, beta 2 is the northeast and north central area, and beta 3 for the south area. But here 9 to 7 is more difficult to interpret because we don't have any benchmark to compare our estimated result with other regions. Okay. Okay, here we have the same equation. We have also here 48, 49, and 46. If we see these results, also the same to the previous one. Okay. By here we have p-value interratio are very small. Here we have t is very high. The dummy coefficient gives directly the mean salary value in these regions, west, northeast, north central, and the south area. Which is better okay, method of introducing a dummy variables. Okay, introduce a dummy for each category and omit the intercept term, or you include only -1 categories with the intercept term. Okay, most researchers find that the equation with intercept more convenient because we can use it as a benchmark, okay, to compare it with other value. Okay. If the categorization does not make a difference by how much is measured directly, the dummy variable coefficient estimate. Testing whether or not categorizations is relevant can be done by running a t-test of a dummy variable coefficient against zero hypothesis. Okay, this is our model. In the previous session, we considered an ANOVA model with one qualitative variable with 3 categories. In this session, we considered another ANOVA model, but with 2 qualitative variables. Okay. Here we have example 9.2, hourly wages in the relation to marital status and regions of residence. Okay, we have 520% in May 1985, and the following regression results stated is in equation 931. Okay, Y is hourly wage. D2 if the respondent are married, 1 for married, 0 otherwise. So in the dummy variable, it is common to use. Okay, for example, we use here the dummy variable. Okay, we have, for example, if we have dummy variable for educational level, 1 for higher education, 0 otherwise. Okay, it is a common in dummy variable model. We use 1 for something, 0 otherwise. Okay, here we can make this category in terms of educational level. Okay, 1 if the respondent, okay, graduated from university. So it could be undergraduate, okay, or postgraduate, okay. And 0, if the respondent graduated from high school or lower. This means from the kindergarten until high school. Okay, we use this one, our data in terms of educational level. If you do not use this one, you can use, for example, for years of schooling. But this is not a dummy variable. Years of schooling, for example, if the elementary school, this means we put here 6. Yeah? In Indonesia, we have 6 years for elementary school. Okay, junior high school, this means 6 plus 3. Sorry. This means we get here 9 years school. This is a compulsory program. Senior high school, this means we have here 6 plus 3 plus 3. This means here 12 years. Okay. We have also, for example, university. This means you have here 12 plus 4 or 5, something like that. You have here 16 because we have a normal university program is 4 years. This means we have 16. For the master degree, we have here 16 plus 2. 16 here, 18. Okay, for the PhD program, okay, we have here 18 plus 5. That means we have 23 years. But this one ratio scale, this one is ratio scale, not qualitative. Okay, it is not qualitative variable. Okay. You get it? Any problem? No any problem? Okay, if you don't have problem, we continue our class here. Okay, in this example, we have 2 qualitative regressors. Okay, is with 2 categories. Yeah. Okay, this D2 as marital status. Yeah, and D3 is residence where the respondents located. Okay, which is the benchmark category here? Obviously, is unmarried non-South residents. Okay, in other words, the respondent who are not married person and who do not live in the South are omitted in the category. So all comparisons are made in the relation to this group. The mean hourly wage in benchmarking is about 8 something, almost $9 per hour. Okay. Compared with the average hourly salary of those who are married in the higher, about 1.1, because 1.0997 is almost 1.1. For an actual average wage of this area, this means we add 8.8 plus 1.09. Okay. By contrast, for those who live in the South, an average hourly wage is lower, about 1.67. So we subtract 8.8 minus 1.67. So we get here hourly salary about 7.14. Are the preceding average hourly wage statistically different compared to the best category? There are all the differential intercept are statistically significant as the p-value are quite low. Okay, we have here for p-value here less than 0.05. Here also less than 0.05. This means all the dummy variables are statistically significant. Because these dummy variables are statistically significant, this means we can make summations between the intercept and the dummy variable coefficient. Once you go beyond one qualitative variable, you have to pay close attention to the category that is treated as the base category, since all comparisons are made in the relations to that category. This is especially important when you have several qualitative regressors, each with several categories. But the mechanics of the introducing several qualitative variables should be clear by now. So if next section is if we group together between qualitative and quantitative variable as regression variables, so we call the results as ANCOVA. Okay? ANOVA model of the type discussed in the preceding two sections are the common in the fields such as sociology, psychology, education, and market research, are not the common in economics, because usually we use qualitative and quantitative variables together in the model. Typically, in the most economic research, a regression model contains both type of regressions of variables. So the estimation result from this model, we call it analysis of covariant, we call it ANCOVA. Okay, here to motivate the analysis, let us consider example 9.1 in the previous example. By maintaining the average salary of public school teachers might not be different in the three categories regions if we take into account any variable that cannot be standardized across the regions. Consider, for example, the variable expenditure on public schools by local authorities as a public education, is primary as a local and state education. So we have here another variable, X variable is the spending on public school per pupil here. So we have equation 9 for 1. So as mentioned in the previous model, D2 is area for northeast and north central. D3 is for the south. That means we have D1 for the west area. Okay, data on X are given in the table 9.1. Keep in mind that we are treating the west as the benchmark category. As soon as beside the two qualitative regressors, now we have another quantitative variables, that means spending on the public school per student. From the table 9.1, the estimated results of equation 9.41 is stated in the equation 9.42. Here we have this T statistic, T ratio for each parameters here. This one for beta 1, this one for beta 2, beta 3. We have here asterisk. For one asterisk is less than 5%, and double is greater value than 5%. Okay, as a result, suggested ceteris paribus, published expenditures goes up, okay, by $1. On average, a public school teacher salary goes up by 2.34. because here we use this variable in terms of category, and the data are not transformed into log term. So we interpret in a unit. Okay. Here, if the public expenditure goes up, increased by $1, means the average public salary, public teacher salary will increase by $2.34 by assumptions other variables remain constant. Okay, contouring for spending on educations, we now see the difference in differential intercept coefficients is not significant for either the northeast and north central regions or for the south. Okay, this here only this variable is statistically significant because this coefficient has 6.5 something of T ratio. This means only spending on the public school variable is statistically significant. Okay. So this one, the estimated result in terms of graph, we have here south area. This one is northeast, the north central, and this one is west. The slope is the same. The different only the intercept. Okay. We can also use the dummy to test whether there is a structural change in the dummy in the data. Okay. Okay. Here we have to use this test to test whether there is the difference between the parameters before and after the shock happened. Okay, for example, here we have here data. Okay, we discussed it related to the relationship between saving and income in the United States over the period of 1970 until 1995. We divided this period into two periods. This means 1970 until 1981 and 1982 until 1995. So this is the basis of your test. There was a difference in the regressions of saving on income between two periods. Okay. However, we could not tell whether the difference in the two regressions was because of difference in the intercept term or slope coefficient or both. Very often, this knowledge itself is very useful. Okay, we use here equation x71 and 72. Okay, there are four possibilities which is listed in the figure 9.3. Okay, first, both intercept and slope the coefficient are the same in the two regression model. This case of coincidence regressions model. Okay, we can see here this one. This is the same for all period. Here, intercept is the same. The slope is the same. Here, the intercept is different, but the slope is the same. Okay, this one for the B. Panel B is the only different in intercept. In panel C, okay, this one, okay, the intercept is the same, but the slope is different. Here, okay, in panel D, okay, both intercept and slope are different. Okay, this one, these are four categories in the short test model. Okay, the source of difference, if any, can be pinned down by the pulling all the observations in the 26 and running just one multiple regressions. So here, if you want, if you do not want to run this all samples in one equation model. So you have to run twice. Okay, first period and second period. But here we can add together with one equations by adding one dummy variables. So here this dummy variable, one observations in the period 1982 until 1995, and before the period is 0. Okay. Okay, main saving functions for the first period is this one, because we set dummy is 0. Okay, and this is a main saving function for the second period. Here we set dummy is 1. So dummy is 1 is alpha 1 plus alpha 2 plus beta 1 plus beta 2x. Okay. Okay, because yeah, okay, if this dummy is significant, so we can add alpha 1 with alpha 2. Okay. If this dummy is significant, that means we can add this one. Okay. Because this one, beta 1 belong to x, and here beta 2 also belong to x. So these dummy variables, if this is different, this means we have different slope. If only this one significant, if D1 significant, this means there is a difference in slope. In the constant in the interceptor. But if dummy is significant, this dummy is significant, but here is not significant, this means this is equation with difference in slope. If D alpha 2 significant and beta 2 significant, this means we have the fourth category. Okay, here, let me explain in this one. Here, both okay, alpha 2 and beta 2 is not significant. Okay, here, only alpha 2 is significant. Okay, here, alpha 2 is not significant, but beta 2 is significant. Here, in the fourth example, here, both alpha 2 and beta 2 are significant. Okay, you get it? This is your test. Any question? Okay, let me continue this explanation. Okay, this is the data here. Dummy before is 0. You can also use for this test in your model. For example, what is the effect of COVID-19 on the demand for money? Okay, the effect of COVID-19 okay, on the demand for electronic money. Okay, here we use dummy, okay, 0 for the period before COVID-19, and D1 for the period COVID-19. Okay. Okay. Well, we call it D19. It is easier to remember. So, if D19 is statistically significant, this means that okay, there is an effect of COVID-19 on the demand for electronic money. Okay, you get it? Any problem here? How to use the Joe test? No? No problem? Are you still alive?
Yes, sir.
Yes,
Okay.
sir.
Okay.
Yes, sir.
I thought
Yes, sir.
none of you. Okay, only ghosts who are attending my class. Okay. Okay. And equation 951, alpha 2 is differential intercept, beta 2 is differential in slope coefficient. Okay. We call it slope differ, indicating by how much the slope coefficient of second period saving function for this example. Let me value is 1. Okay, different from the preceding period. Okay, notice how the introduction of dummy variable in the interactive goes. If you want to get interactive, for example here, let me explain by this whiteboard. Okay. Suppose here we estimate the demand for money before and after, before and during, not after here, still during COVID-19 in Indonesia. Okay. So first, we have to formulate the standard demand function. So okay, here we have money demand. It's a functions of income, interest rate. Okay, if we estimate this a nominal money demand, we have here price. Okay, then if we want to test whether there is an effect of COVID-19 on the demand for money, okay, we have to include this dummy variables. Yeah. I and P here. Okay, and then we add dummy. Okay, here this dummy. Okay, only the effect on intercept. If this variable is statistically okay, if we have this equation in our model, okay, because because COVID-19 can have effect on the income also, so we multiply here dummy with income. Yeah, we have this equation. This means here dummy, yeah, has the effects on, okay, effect on intercept and slope coefficient. Okay, if in your theoretical review you get that this okay, this COVID-19 not only have an effect on the constant and income, but also on the prices. So you have here dy I D. Sorry, here. Okay, sorry, I forgot here we have another Y here. Sorry. Okay, another Y here because we have multiplication dummy with Y here will come. Okay, here D. Okay, we multiply here. We have, sorry, here we miss one Y here. D with P here, and P also, and D. Okay, this means this dummy has effects on intercept and slope. So here slope coefficient is Y and price. Okay, these two variables here. Okay, here we call it is this type is multiplicative or interactive form. Okay, you get it? No?
So,
Okay. So this is for the estimated results for the equation 951 is stated in the equation 954. Okay, here this asterisk, one asterisk indicate that the p-value is less than 5%, and double asterisk indicate p-value greater than 5%. That's mean if one asterisk is significant, double asterisk is not significant. Here we can see that here the dummy for the constant, because it is significant, so we add 1 point something with a 4 point something. Here dummy is also significant. This is multiplicative, so we add 0.08 something minus 0.06 something. Okay, here y hat, okay, from the 954 we derive equation 952 and 953, which are saving income regressions for the first period, this one for the second period. Okay, these are precisely the results we obtained in the equation X71A and X712, which should not be surprising. These regressions are already shown in the figure 8.3. What are the advantages of the dummy variable technique? Okay, in the equation 951. Okay, or for the two tests. Okay, we need to run only a single equation model instead of double or two regressions model. Okay, if you use two tests, we can save time. Okay, we can have more time to analyze our data because only one equation need to be estimated. Okay, the single regression can be used to test variety of hypotheses. Thus, if the differential intercept coefficient alpha 2 is statistically insignificant, we may accept the hypothesis that two regressions have the same intercept. Okay, this is how to use this Chow test. The Chow test does not explicitly tell us which coefficient, intercept, or slope is different, or whether the sample both are different in the two period. This is one can obtain a significant Chow test because the slope only is different, or the intercept only is different, or both are different. Okay, in other words, we cannot tell via the Chow test one of the four possibilities depicted in the equation in the figure 9.3 exists in the given example. Okay, finally, since pooling is we estimate together in one equations. Okay, increase the degree of freedom because we have more sample size with the same parameters. That means we have higher degree of freedom. If we have higher degree of freedom, this means we can get more precise results. Okay, interactions even using dummy. Okay, this is the same here. This dummy variables. Okay, this is female, non-white, and non-Hispanic, etc. You can read by yourself here. Okay, you have double. This means you multiply these dummy variables. Okay, okay. This means here we have D2 times D3. D2 times D3, we have here D2 is gender, D3 is color. Okay, yeah, white. This one, okay, 1 for female, 0 for otherwise, 1 if non-white and non-Hispanic, okay, and 0 otherwise. So this, if we multiply the 2 and the 3, we have two interactive, multiplicative, additive functions. Okay, this one example 9.5. Okay, the regression results based on the model 961 using the data that were used in the regression equation 931. We have here, okay, this one single dummy, and so single dummy. Still, one asterisk is 5% significant. If double asterisk is not significant. Okay, here we see that this one, this means if one is female, okay, okay, this one earning for female is lower compared to the men. Okay, because men is 0. If he is 0 here, this means this is a benchmark for the men. Okay, men, and this one 0 also. Okay, men for non-white and non-Hispanic. Okay, this one dummy 3 is for non-white and non-Hispanic. Okay, now consider result 962. Okay, we include the interactions, dummy interactions, dummy 2 multiplied by dummy 3. Okay, this means here, okay, 2 additive dummies are still statistically significant. Okay, this one significant, this one significant, this one is not significant. Okay, okay. If you think this is a low enough probability, then the result equation 965 can be interpreted as follows. Holding level of education is constant. If we add the 3 dummy categories, we will obtain that minus 1.9 something, which means that mean hourly wages of non-white, non-Hispanic female workers is lower by 1.96. Okay. Okay, which is between the value of minus 2.3, this one, gender difference alone, and minus 1.7 something is race difference alone. Okay. Okay, we can also use the dummy for the sessional. If we have 4 sessions, this means we include only 3 sessions. As explained before, if we add all the dummies, including interceptance, we have a dummy variable trip. Okay, I don't know to explain clearly this one. You can read by yourself. Okay, same. You cannot use all dummies together. Here only dummies without interceptor. Okay. Okay, you can read this one. Simple 9. This one dummy quarterly. Okay, same. We have here D1 is dropped from the equation. Okay. Theorem, precise linear regression. piecewise regression explanation is how to drop one variable or more. Okay. To illustrate yet another use of dummy variable, consider figure 9.5. We show how a hypothetical company remunerates its sales representative. It pays commissions based on the sales in such manner that up to a certain level, as target level or threshold level, there is one stochastic commission structure, and beyond that level another. Okay, this one piecewise. Okay, we have two category here. This one is lower one. This one is higher one. Okay, this one. Okay, we have here. Okay, piecewise regressions. Okay, this is a target. Okay, data on the commission sales and the value of threshold level. This one threshold level. Okay, the technique of dummy variable can be used to estimate the different slope of the two segments of the piecewise linear regression shown in equation 9.5. Here, Seller's equation, Seller's summation, Xi is a value of sales generated by salesperson. X asterisk is the threshold value of sales known as the not known in the advance. This is a target of this each salesperson. D1 if the salesperson can sell more than the target. D0 if the sellers cannot sell more than target. Okay. Here, if D1, Di is 0, there's these equations. If greater than, if the sellers can sell greater than target, this is the equation. Okay. Okay. Here the difference. Okay. Between only standard model, this one with the target. Okay, you can read by yourself this one. Panel data. Panel data will be discussed in the panel data will be discussed in the